Welcome back to another explainer. Now, before we really get into it, I think we need to just take a second and celebrate. Because we actually did it, everyone. We finally united the tech world. We killed off the dreaded micro USB, we banished those weird proprietary barrel jacks, and threw out all those fraying legacy cables. We are finally living in the utopian future of the universal USB Type-C connector. But before we pop the champagne, I kind of need to break some bad news to you. While the outside of these cables is a beautifully universal, identical utopia, the inside? Yeah, the inside is a terrifying, chaotic labyrinth of protocols. Today, we're cracking open the 2026 technical analysis of USB Type-C architecture. And honestly, by the end of this explainer, you will never look at a piece of copper wire the same way again. Okay, let's kick things off with a scenario we've literally all lived through. Picture this, you just dropped some serious cash on a shiny new 2026 laptop. You're super excited to hook it up to your gorgeous new 4K monitor. So you grab a random USB-C cable, maybe you bought it at a gas station, maybe you just found it tangled at the bottom of a drawer, you plug it in, and absolutely nothing happens. Your screen just stares back at you in the dark. Or worse, your laptop throws you one of those passive-aggressive operating system warnings about slow charging. Why does this happen when the plug physically fits perfectly? Well, it's simple, because your cable is essentially lying to your face. Which brings us to Section 1, the Great Type-C Illusion.
The core problem here is that the 24-pin oval connector looks perfectly identical across every single device. It's wonderfully symmetrical, you can't plug it in upside down, but that physical homogeneity is a total facade. Just because the metal plug has 24 pins doesn't mean the manufacturer actually wired them all together inside the cable. Think about your basic USB 2.0 Type-C cable. You know, the cheap one that comes free with your phone. It only has 4 active wires: power, ground, and 2 incredibly basic data lines. It is the digital equivalent of a 1-lane dirt road. But contrast that with a fully featured superspeed or USB 4 cable. This thing is a 120 gigabit per second multi-lane superhighway. It's packed with highly complex twisted pair engineering, high-speed differential pairs for gigabit transmission, and sideband use pins. When you buy a cheap cable, those extra 20 lanes aren't just turned off. They are literally physically missing inside the plastic casing.
All right, moving right along to Section 2, data, power, and e-markers. Let's do a quick digital autopsy. Because the numbers we're dealing with in 2026 are absolutely staggering. Just look at this, 120 gigabits per second. To achieve this massive asymmetrical bandwidth, engineers had to throw out the old binary way of sending signals. They moved to something called PAM3, which actually transmits data across 3 distinct voltage levels, -1, 0, and +1. It's kind of like upgrading a simple on-off light switch into a complex 3-way dial, letting you send 50% more data per clock cycle. Now, if you try to shove a USB 4 signal down one of those cheap gas station cables we just talked about, it will fail instantly. There's a catastrophic lack of high-speed lanes and 0 shielding. It's essentially digital suicide.
But hey, it's not just about pushing data. It's about pushing raw power. 240 watts. We're talking about the extended power range, or EPR. That is 48 volts at 5 amps being shoved through a wire that is literally no thicker than a shoelace. We are way beyond just topping up your smartphone battery here. This is enough juice to power high-performance gaming rigs, run localized servers, and literally charge electric bicycles. But pushing that much power requires some serious heavy-duty engineering. We're talking specialized wire gauges and advanced insulators. Because if they get that wrong, the cable doesn't just fail, it literally melts right there on your desk. So how exactly do we keep those 240 watts from, burning our houses down? Enter the hero of our story, the e-marker. Any cable designed to carry more than 60 watts absolutely must have this microscopic integrated circuit embedded right inside the plug housing itself. I like to think of the e-marker as an unbribable, heavy-duty nightclub bouncer for your electrons. When you plug your laptop into a massive power brick, the system immediately asks, hey, can this wire actually handle 240 watts? And if the e-marker isn't there to vouch for the cable's thermal tolerances, the system safely and aggressively throttles the power cap right down to 60 watts. It's a silent protective intervention going on behind the scenes to prevent thermal runaway and fires. Pretty wild, right?
So how does that conversation actually go down? It all happens on something called the configuration channel, or CC pin. This single pin acts like a super tense diplomatic negotiation between a boss and an employee. First, it detects which way you flip the cable. Second, it establishes a super safe baseline 5-volt trickle charge. And finally, it executes a biphase mark coding digital handshake. This handshake is absolutely crucial.
It dictates exactly who is providing the power, who is receiving the power, and who gets to be the host of the data. And the craziest part? All of this happens in milliseconds before a single byte of your actual data even starts moving. Let's pivot slightly for Section 3, black screens and active cables. Let's step away from the hardcore physics for just a second and go back to our everyday annoyances. Remember that black screen tragedy with the new monitor we talked about earlier? Well, Type-C is amazing because it has these things called alternate modes. This means it can actually repurpose its data pins to speak completely non-USB languages, like DisplayPort for your video. But, and this is a massive but, to natively transmit those uncompressed 4K, 8K, or 10K video streams, it relies on those extra high-speed copper lanes. Your basic charging cable literally, physically lacks the copper required to carry that video signal. You are trying to drive a massive freight train down a tiny bicycle path. It is just a physical impossibility. And listen, even if you do have the right copper, you still have to fight the laws of physics. For a standard passive cable, maintaining an 80 gigabits signal is practically impossible once you go past about 0.8 meters. The signal simply degrades, flatlines, and dies. So if you want a cable that's actually long enough to reach from your PC all the way to your VR headset, you are going to need an active cable. These cables have literal silicon chips. They're called retimers and redrivers embedded right inside the plugs. A retimer will catch a dying, degraded signal, extract the core data, and synthesize a brand new, pristine signal to blast down the rest of the wire. It's literal silicon necromancy, resurrecting your data from the dead.
Okay, let's zoom out for Section 4, global market cable philosophies. We know the technology is incredibly complex, but how do these massive tech companies actually sell it to us? Well, it mostly comes down to regional geopolitical tech philosophies. Over in North America, heavily driven by Apple and Intel, the philosophy is what they call invisible complexity. They want premium parity, so they over-engineer their cables to Thunderbolt 4 and 5 standards, charge you a massive premium, and basically guarantee that anything you plug in will just work flawlessly at maximum speed. Now, in Europe, the driving force is entirely different. It's all about eco-guilt and sustainability. They prioritize post-consumer recycled plastics, extreme physical durability, and the right to repair to minimize global e-waste. Meanwhile, over in the Asian market, it is the wild west of hyper-fast, proprietary chaos. Brands over there are pushing 240 to 300-watt charging protocols that require their own specialized pins. This creates massive hyper-segmentation. You can buy a perfectly optimized bedside charging cable for absolute pennies, but if you try to use it for data, it won't transfer a single file worth a darn. Because of all this, consumer confusion is sitting at an all-time high. But to fight back against this madness, European regulations now mandate clear, transparent iconography directly on the cable itself. You don't have to guess if a cable can handle 240 watts or 40 gigabits per second anymore. It's literally printed right there on the plug. It totally cuts through all the ambiguous marketing jargon, and honestly, I think we can all agree this is a total sanity-saving measure that the rest of the world needs to adopt, like, yesterday. Which brings us to our final part, Section 5, the ultimate survival guide. All right, we've fully diagnosed the illness, now I'm giving you the cure. How do you, the informed consumer, navigate this digital minefield? Honestly, treat this expert selection matrix like your sacred text for 2026. If you just need to charge your basic phone on your nightstand, buy a nice, long 4-meter USB 2.0 cable. You absolutely do not need an e-marker, and it's going to be dirt cheap. But if you are powering a high-end workstation laptop, you need a 240W EPR-marked cable, and you need to cap it at about 2 meters. Need to run a massive 8K external display? You've got to step up to USB 3.2 or USB 4 and keep it under a meter unless you want to pony up for an active cable. And for extreme high-speed storage or an external GPU, you absolutely non-negotiably need an 80 gigabit USB 4 version 2.0 cable with an e-marker, and trust me, it's going to be very short. It's all about matching the specific tool to the specific job.
But if you're like me and you kind of hate looking at charts and you just want the ultimate future-proofing cheat code, here it is. Just spend the money up front on an officially certified USB 4 or Thunderbolt 4 cable that explicitly supports 240W EPR. Look for the actual official certification logos on the box. Yes, the initial cost is definitely higher, but this is your true one-cable-does-all solution. It mathematically eliminates the risk of a protocol mismatch, device throttling, or, melting a cheap wire onto your rug. It is absolute 100% peace of mind.
As our source material so perfectly summarizes, its physical simplicity is a facade masking a highly complex, layered architecture. We look at this little metal oval and we immediately think, oh, that's simple. But in reality, the humble USB-C connector has evolved into a heavily disguised digital processing superhighway that is routing massive amounts of power, uncompressed video, and gigabits of data dynamically, all in real time. When you really dig into it, it is honestly a total engineering marvel. So I'm going to leave you with this final thought. Armed with all this new knowledge of E-markers, twisted pairs, superhighways, passive signal degradation, and intense power delivery handshakes, let's be real. Will you ever look at a random unmarked cable sitting in a coffee shop drawer the exact same way again? Yeah, I didn't think so. Stay sharp out there, always read your specs, and hey, thanks for exploring this labyrinth with me. See you on the next explainer.